Hi, hello everybody. Thanks, Ben. I appreciate the introduction. Um, all right, I guess let's get right into it. Um, Today's talk is going to be pretty much about my dissertation research. I thought, what can I come to the table here with and avoid telling you all about things I shouldn't be telling you all about. This research is pretty much on the tail end of everything. We're still working on getting a few results, exciting results out, but here I am, and I'm about to tell you about it. And like Ben said, I'm currently at USF, and I guess the slides will tell you about that. So first, a little about me. Um, I didn't have time to put the best about me slides together, but I recently went to middle school to tell little kids about eighth graders about science, and in that talk I showed them these slides. So forgive me if they're a little quirky, but here's a little about me. This is what I told them about. So my name is Pierre, and I come from a country called Syria. Um, and it's here on the map. A little about me, and again, excuse the silliness, but this is what I was telling the eighth graders about. I'm a computational polymer physicist. I study polymers. Um, I imagine most of you know what those are. It's just long chain molecules. I'm an engineer and a scientist, and I do experiments on a computer. All right, so let me tell you a little more about my history before we get to the fun part. Um, just showing them that I used to be a kid like them. um, then I did my Bachelor of Science at the American University of Sharjah in the UAE, where I grew up. Then I also did my master's there. And then finally in 2017, I moved to America, where I worked on my doctorate of philosophy and chemical engineering with Douglas R. Tree. And then finally now I've moved to Florida. I like the weather here much more, as you can imagine, to the University of South Florida, where I'm working on my postdoc. Here's a little bit about the research that I've done in my long time in school now. I started off with a capstone project where we worked on enhanced oil recovery. I don't remember much of that project. I'm not sure how much real work I did on that anyway, so maybe that's for the best. But in my master's, I worked on smart drug delivery systems to deliver chemotherapeutic drugs to cancer. I could tell you a little bit about that if there's interest. What I'm here to talk to you about, of course, is my PhD work, where I worked on the simulation of polymer crystallization. And then finally, here at USF, I work on uh, understanding toughness in filled rubber. And we can touch on that too if there's interest again. So a little more about me from these slides. Uh, Maybe this is a nice idea to tell y'all about me too. I loved chemistry when I was in middle school. Um, Here's a little about my music. I really enjoy hip hop and rap. So I was just funnily enough, as you can imagine, this was the crowd favorite for the kids. I really like Indian food. And here's some pictures of me hanging out with fellow scientists and friends. All right, moving on. So let's get to the cool stuff. This talks about polymer crystallization. My entire PhD dissertation was about polymer crystallization. Why do we care? Well, as you can imagine, uh, polymer crystallization is important because of its prevalence in today's markets. It makes up 260 metric tons per year of industrial production. And given that, although it's a classical problem that has been worked on for several years, small improvements in our understanding of polymer crystallization really does matter, right? And additionally, we can touch on this a little more. It's really important when we think about recycling and such problems that we understand crystallization, specifically crystal nucleation. And let me motivate this a little further. Why do we care about polymer crystallization? Well, because it affects the final product quality. So here we're looking at, on the bottom right here, we're looking at three different examples of polyethylene. And these different examples of polyethylene have very different strength or toughness, right? You see that on the y-axis here. Um, on the lower end of crystallinity, you have something like grocery bags, right? LDPE. But on the higher end of crystallinity, you have something like dynamo, which is actually the world's strongest fiber. Chemically, both of them are polyethylene molecules. Um, and a big reason why you have this difference in the properties is because of the crystallinity. So we care about this. We care about this because of its prevalence in industry and how it affects properties. Um, I just want to say, Ben, feel free to interject at any point if you feel like you have any questions, or actually if anybody asks questions in the chat, uh, yeah, I don't really mind. All right, okay. So a little more on crystallization. It's a multifaceted process, right? You can see that here by the multi-scale images. So, when these crystals grow, you see these big spherulites form. Um, and this process by which this forms is multi-scale, as you can see here on the right. There's different length scales that are important, and different length scales and time scales. There's different resulting morphologies. So it's an interesting problem to work on from a physics standpoint. All right, so let's motivate this further. There's some results, let's say, that show you that anyone that's familiar with nucleation and first order solidification can tell you that classical nucleation theory is how we analyze these systems. So what classical nucleation theory is, it's basically a model that you can use to predict nucleation rate, right? So how long it takes something to nucleate a new phase. How do you go from a metastable melt to a crystal or a solid? So if you're looking here, well, the rate depends on the free energy. So actually, classical nucleation theory is a model for the free energy of crystallization, right? So imagine a situation where you have a temperature lower than the melting point, right? So what you've done is you've taken a melt of polymers. Here you see it. You see that on the left here. You quench it below its melting point. Now what's going to happen? Right now there's a driving force, a thermodynamic driving force to crystallize or solidify. So given this, what this disordered liquid is going to want to do, of course, it's going to want to move to a lower free energy state. That's what thermodynamics tells us matter likes to do. And of course, the free energy is lower because you're lower than the melting point. But what classical nucleation theory tells us is when moving on this x-axis of crystalline order, when increasing crystalline order, it will first face a nucleation barrier, right? So essentially, to go from the metastable state to the stable state, it has to overcome some free energy barrier. It has to go somewhere it doesn't really want to go. In other words, somewhere that is thermodynamically unfavored. And how does this happen? Of course, we know there's thermal fluctuations in nature, and eventually a thermal fluctuation will bring enough segments of the polymer into a crystalline phase that will, slip down this slippery slope. All right, so the problem with this picture is that there's a bunch of results from experiments and simulations, as we shall see, that tell us that maybe this process isn't actually a single step process. And for example, here I have some examples. So Saxon wax, you use X-ray scattering to probe order at the molecular level and at the chain level. And what they find is that there's some sort of other form of order. It's actually a pneumatic order that forms before crystalline order. There's a melt memory that tells us maybe there's a complicating the picture. And then finally, there's direct observations of precursors to this crystal I show you up top, right? So what this motivated is the SOM hypothesis, where you had a couple scientists, and you see the papers down here, that proposed alternate theories that tell you, no, it's not crystal order on the x-axis first, it overcomes the barrier in pneumatic order. So let's talk about what pneumatic order real quick. is real quick, because it's important for everything we're about to see. So unlike the crystal here, where you have a crystalline lattice, here you have a crystal, a nucleus come together, but this nucleus is one that has elevated chain level order, right? It has parallel chains. And once that happens, it can move down the slope down to the stable crystal. All right. So given that these models that are, well, well, essentially the controversy comes from the fact that which one is at play, which one which theory is the better one to describe crystal nucleation. Given this, and given that both theories suggest a free energy landscape, maybe a way forward is to calculate that free energy landscape. So that's exactly what we did, and that's what motivated much of this PhD dissertation. We're like, okay, we're not going to use molecular dynamics, which most folks use, because molecular dynamics introduces all of these traps that maybe don't allow us to reach equilibrium answers. So essentially, we're going to use Monte Carlo, which I'll tell you a little bit about shortly, and hopefully use that to identify the stable phases and the phases at play, and study crystalline nematic order together and build a 2D free energy landscape. All right, and here on the right, you see kind of the picture that we're proposing. We use two Monte Carlo advanced sampling Monte Carlo methods to build phase diagrams and to build free energy landscapes. So here's the outline of the talk. First, I'll tell you a little bit about molecular simulation. In giving this talk, I know that many people perhaps have aren't experts on molecular simulation. So I'm going to touch a little bit about that. I see a question in the chat. Does understanding crystallization of polymers have potential applications? Right. Yeah, it does. You can imagine that. Understanding crystallization, a lot of these molecules that are in the solid phase, a lot of these materials that get thrown out are actually mixtures of different polymers together, and that's the challenge really of recycling and upcycling. Is if you have a polymer and then it gets thrown in a landfill, it's going to be mixed with all sorts of other polymers. And now how do we go and pull back that raw material? And understanding crystallization better, although not directly, is going to give us ideas about how to process these solids that have some crystallinity, right? The first step is, of course, to melt them, right? So perhaps if we can understand crystallization better, we can use this melting and solidifying cycle to selectively separate these molecules. And there's a bunch of experiments that suggest that you can do that via crystallization. Yeah, so I hope that answers the question. So anyway, moving on. I guess let's jump right into it. So how do we simulate a homopolymer like polyethylene right in a lab? You buy polyethylene and you process it, not to diminish what people do in labs. I think that my work is far easier. But how do you simulate homopolymer like polyethylene? Where you can simulate it on many scales. Of course, polyethylene is just ethane repeated, right? For some large molecular weight. So one way you can do it is you can define explicitly the carbons and the hydrogens and then define how they interact. In crystallization, we are not interested in resolving what the carbon and the hydrogen interaction is, or maybe what the bonded carbon interaction is. So sometimes you can elect to combine some of these monomers in a bead, right? And that gives you what's called a bead spring simulation. Right, so you lump a bunch of carbons into a bead, and then you connect these different segments. So this all comes from theories of polymer physics that allow us to do this magic. Of course, as you can imagine, in each of these beads, I have now reduced 1, 2, 3, 4. So 4 times 3, that's 12. It'll be pretty embarrassing if I'm doing math wrong live. But essentially, you've gone from 12, 12 numbers that you have to calculate for to a single number, right? And as you can imagine, with the molecular weights that you're encountering in experiment with these molecules, that's going to save you a lot of time. So here's all atom, right? When people say they're doing atomistic simulations, they're doing these kinds of simulations. And then, here's coarse grained polyethylene. And of course, what you'll do is you'll connect a bunch of them. And that's exactly what we do. We actually lump 4 CH2s into a single molecule, into a single bead. And then the beautiful thing about Monte Carlo is instead of solving Newton's equations of motion as people do in molecular dynamics, what you can do is you can be you can play fast and loose with some rules and evolve the system from state to state with some smart polymer specific moves, right? As you can see here, for example, if we look at reptation, which we know from polymer physics that a polymer chain moves like a snake. Essentially, what happens here is you remove a bead from one end and you introduce it on the other end, right? It's slithering much like a snake. So anyway, that's kind of a benefit of Monte Carlo. Now we've introduced coarse-grained polymer model. You define initial positions. You define a periodic boundary condition, so things can move from one end to another, and you have a semi-infinite fluid. And then you define a move set, bada bing, bada boom. And you also have all sorts of stuff that you can introduce here, and we can talk about them if questions come up. But that's a Monte Carlo simulation. All right, let's get to the fun stuff. So here, we're going to talk about nucleation and semi-flexible oligomer. Funnily enough, this is not really, as you can imagine, this is not really a chronological, the order of things. In fact, we started off trying to introduce a GPU-accelerated polymer-specific Monte Carlo code, but that didn't go as well as planned, which might as well be the subtitle of every PhD dissertation. So instead, I'm going to tell you about the rest of it is actually chronological. I'm going to tell you about nucleation, semi-flexible oligomer. We're going to look at some free energy paths, and then we'll move on to, I guess, checking the sensitivity of the result I'm about to tell you about. So we started with a simple model of semi-flexible oligomer, right? We've lumped these carbons into a single bead. And now how do these single beads interact with each other? So first of all, we chose the simplest way that they can interact with each other, that non-bonded beads can interact with each other. That's the hard sphere repulsion. So either they are far apart and they don't interact, or they're on top of each other and they repel each other infinitely. We have rod-like bonds. So what that means is you have these, I keep trying to explain things, and then I remember that, with my hands, and then I remember there's no video. And then you have rod-like bonds. So what that means is there's no movement on the bond scale. They're just bonded at a single equilibrium length. And then finally, a stepwise bending stiffness. So what that means is that either you're larger than some angle and you are not stiff, or you are smaller than that angle and therefore stiff, right? So if it bends too much, if 3 beads bend too much, then there will be a penalty for that. And then if they stretch out, right, and this is just what a stiffness of a chain is. Actually, because of the bead spring nature of this, also encodes the dihedrals as well. All right, then I put that in a box, much like I said before, and I simulate it. All right, so if we're talking about the specifics, just a little more boilerplate stuff to get into here. What are the orders? What are the degrees of freedom that we have here? Well, there's the volume fraction, right? So how many beads I stuff in my box, and also the reduced temperature. So the reduced temperature is just reduced by this stiffness scale. So essentially, it's the Boltzmann temperature divided by the stiffness scale. So those happen to be the 2 degrees of freedom. And what you see here in front of you on the right is just the persistence length of the chain, right? At high temperature, the chain is actually not stiff, and at low temperature, the stiffness increases to some plateau. So temperature encodes the stiffness as well. It's like an inverse stiffness. All right, so I guess a little more boilerplate stuff here. So let's talk about phase diagrams. Um, in this first one, so how do you build a phase diagram? So hopefully I can walk you through this. So we've talked about polymer models and all that stuff. Now let's talk about what Wang-Landau Monte Carlo, which is an advanced Monte Carlo algorithm, actually does. So essentially, there's this thing in statistical mechanics or thermodynamics called density of states, right? So in this case, we're describing a state as an energy state, right? So for each energy state, you have a density. And what that means is essentially like how probable is that state, right? So in this fictitious density of states that I show you, the most probable state is the state in the middle, right? So what replica exchange Wang-Landau Monte Carlo lets us do is essentially you start off with a guess, right? And you see that in the red. So essentially what this means is you guess that all the states are equally probable. As you iterate through this process, what essentially you're using this density of states to accept or reject states, and over time you are going to approach the real density of states. When you do, you can treat that density states like a microcanonical partition function. Essentially, what that means is that it codes all of the temperature behavior of the system. It's the probability of a state, right? So what you can do is use this information to get all sorts of things, including the heat capacity. And the beauty of a heat capacity, of course, is that it will encounter a peak at any transition. And of course, we're trying to study solidification of polymers. So the first step is, of course, identifying where transitions happen, right? So here you look at some heat capacities, right? So we sweep volume fraction. As you can remember, the 2 degrees of freedom were volume fraction and reduced temperature. We sweep volume fraction. Each simulation gives us the result for all of the reduced temperature, and we get the heat capacity, right? And what we see here, as we sweep the volume fraction, we see that we at low volume fraction, we have a peak at every volume fraction, right? It's encountered at some transition temperature, but clearly this peak, is encountering some sort of change other than its position and temperature. We also see that it's broad at low phi or volume fraction, and it gets more narrow and has a higher amplitude. All right, so let's look at a little more at let's investigate what we're looking at. So 2 things we use to study our phases these are our 2 order parameters, right? They tell us how ordered or not our system is. And the reason we chose them is because as I've shown in the motivation, the 2 things that are important are crystalline order and nematic order, right? Crystalline order is how do beads fit into a crystalline lattice, right? Whereas nematic order is how do the chains align with other chains, right? Let's look on the left here. Crystalline order, as you can see, depends highly on temperature and density, right? At high temperature, you have a melt, it's isotropic, there's no real crystal, right? But as you decrease the temperature, we see that for some phi, increases, but for some it doesn't. Whereas when we look at nematic order, we see that no matter the transition, no matter the phi, we see an increase in nematic order. You can kind of see what's happening here already. So a high T, you see, of course, a nematic order close to 0, which means the chains are randomly oriented. There's no real collective direction that they're all pointing. And at some temperature, which happens to be the temperature of the peak in the CV, we have some sort of increase to almost 100% for the first highest, for the 3 highest densities, and then it kind of cools off for the other. Well, it only increase the increase isn't so drastic for the lowest 2 densities, rising only to not complete to complete nematic order. So much of this data is in published work, which you can access. Hopefully, this video works. It really depends on the month that it does. But let me show you visually what these phases look like. So a high temperature and really any volume fraction, the system is an isotropic melt. Well, okay, I guess it would have been asking too much. Anyway, I have a video here of it just behaving like a liquid. So this is a liquid, right? It's just, there's no real crystal order, repeat unit, and there's no real nematic order. Oh, I hate that the video doesn't work. It is what it is. And on the bottom left here, you see the structure factor. So essentially what we did, just like people do an experiment, you do X-ray scattering and you get back a pattern, a diffraction pattern. And here we have a diffraction pattern. In X-ray scattering, they go and they process the signal. What we have is we have actual positions. So what we can do the same thing they do, or the opposite of what they do, and get a diffraction pattern. And what you can see essentially here is no real pattern. It's just circles, which tells you that it's a liquid. Now, when we look at low temperature but low density, right? We're looking at low density. You see a nematic phase. And the video doesn't work. So in this nematic phase, you have chains that are aligned, but there's no real crystal order. And you can see that in the diffraction pattern, that there's some sort of alignment in the XC plane, but that there's no crystal lattice. So now when we look at the low T and high density, we see a crystalline system, right? So this is a diffraction pattern that you expect from a crystal, right? Because you have repeat units. And you can see here, well, I wish I could rotate it. It's a shame. All right. But you can see here that it's higher order than before. Essentially, if you rotated it, you'll see a gap through the crystal because of the repeat unit. All right, so if we take all of these data points, right, so we have multiple densities, and at these multiple densities, we have either a crystallization temperature or a nematic, isotropic to nematic transition. So if we take those, we put them on a volume fraction versus reduced temperature plot, what we get is a phase diagram, right? So you see here that that we have a high temperature phase and we have a low temperature phase, right? So at high temperature and really any volume fraction, you have an isotropic melt. So what that means, of course, is we've discussed, no real order. Depending on where you are relative to this dashed line, the critical phi, if you're below it, as you cool down your polymer, you get a nematic phase, so only chains align. And if you're above phi crest, what you see is that you encounter an isotropic to crystal transition, right? Your chains become parallel and you also fit into a crystal lattice. Okay. This is a good time to stop if there are any questions. The 1700 microteslas seem high. I'm not sure. All right. All right. All right. So that is it for me.
Yeah. I do have one question. This relates to the when you're talking about how you simulate the polymers. Um, is it feasible to simulate deformation of the individual spheres? So you were talking about having kind of rigid spheres and the bonds that didn't flex or anything like that. Can you add deformation of the spheres and do things like the material maybe softens without fully melting, things like that? Or is that computationally too
It's not.
intensive?
It's not. So can you deform a system of polymers? Yes, of course you can. I mean, um, we do these simulations. Well, by we, I mean the scientific community. I actually do them as well. As I'm saying, my current project is studying the toughness in these in rubber, right, in filled rubber. So essentially, what we do in these simulations is we take a polymer and we stretch it, right? And they look pretty cool. I wish I could show you. Maybe I will after we get done with this if there's time. So you can do that. Um,
Okay.
but there's a second dimension of your question, which is, can you do that with these rod-like bonds and these hard spheres? I think you can. I think you can. I mean, really, what you want to think about, Ben, is like, although they are rigid on a single bond level,
Mm-hmm.
right? You can still stretch them out, right? You can still, right? Let's look at examples here. Um, Yeah, I mean, look here, right? Those polymers are coiled up, right?
Yeah,
So
exactly.
imagine as you pull, what'll happen is they'll stretch out, and this stretching out uh, will have a well, it'll give you a stress response. So essentially, we do what people do in experiment. An experiment you'd like pull on it, or maybe introduce some flow, shear it, and get a stress response, right? For some sort of deformation
Mm-hmm.
rate
Mm-hmm.
or amount, we do pretty much the same things. We replicate real behavior. Those simulations are called non-equilibrium molecular dynamics, where people do that.
Okay.
So you can.
Okay.
Yeah. Interestingly, I'll touch on this question a little shortly after we get to my conclusion slide, because I think you'll see that. Well, I guess you can guess already, Ben, that like because I'm giving so much importance to nematic order,
Yeah.
that stretching it makes crystallization very, very interesting. Um,
Okay.
so so we'll see a little bit about
All
that
right.
later.
All right. Cool. I
Um,
got something to look forward to
yeah.
then.
Yeah. Well, thank you. That's an excellent question. Excuse my excitement.
No, look, that's the whole point. That's what we're going for.
All right. So yeah, so we've talked about the phase diagram, right? I've showed you this phase diagram. Cool, blah blah blah. People have built phase diagrams before. Let me show you what some a real contribution that we've done in our simulations. So essentially, we've adopted another advanced sampling technique called extended ensemble density of states. What that allows us to do is instead of defining states via some energy, we can define states via some order parameter, right? So instead of having a density of states here on the left-hand side or on the y-axis, we have an actual free energy dependent on some order parameter. And much like before, right, you define every state as equally probable and you iterate, and it finally gives you an estimate of um, the real free energy, which I think is so cool. Um, so our algorithm incorporates two order parameters. So instead of having a partition function be a function of xi, some order parameter, and temperature, I'm going to use the two order parameters that I care about, right? Crystal order and nematic order, as we've seen. All right, cool. Um, So now, let's look at different parts of our phase diagram and show you these free energies, right? So now we're looking at a low density at the melting point, right? So right here. So let's explain this figure. This will take a little bit of time, but trust me, it's worth it. So what we've got here on the y-axis is we've got nematic order. So essentially, on the lower side of this graph, you are not stretched out. And on the higher side of this graph, you are stretched out, at least relative to the lower side of the graph. On the x-axis, if we move from left to right, we either go from no crystal order or low crystal order to high crystal order. As you can see, this range is pretty narrow, but let's talk about a specific point in space and describe it. So this point in space is at an intermediate nematic order and at the lower end of crystal order, right? Now it's colored, this is a contour, and it's colored by the free energy value that we encounter at that point. So red means high free energy, blue means low free energy. And free energy, the point of free energy, why we like free energy is because it tells us about what states are favored. If you have a low nature, much like it tries to maximize its entropy, it tries to minimize its free energy. So at a low free energy, that is a desirable state. The highest free energy is the most undesirable state. So what does that tell us, given all this information that I gave you? At low free energy, Well, the two lowest free energies are the coexistence states. So why do we have two states? Because we're at the transition, right? So the isotropic melt is right here, and the nematic phase is right here, right? You are at the transition point, and what you're seeing here is the isotropic melt and the nematic phase being both stable equally, right? They're both at zero free energy. And then what we see is that this is the most undesirable state, right? It has the highest free energy. And what we see is a barrier, right? So as we move up from the isotropic melt with low crystal order and low nematic order, as we move up, we encounter a free energy barrier, but then we get to the other state, right? So you have this barrier. And importantly, in a nematic transition, I to N is isotropic to nematic, there's no movement in crystal order. You just move in, actually, I just remembered that I have some visual aids, right? that would have helped our discussion. So you have the melt here, you have the nematic phase here, and the minimum free energy path, right? Nature dictates that we move in the minimum free energy path. So essentially, any system will like to move from these two phases by a straight line with no real movements in crystal order. So now this picture is very different from hyphae, right? So if we're looking at a point in the phase diagram where we have a crystal transition from an isotropic to a crystal state, again, we have nematic order and crystal order. Now note, right, that the order, here we're going from almost 0 to 0.97 and from a large range of crystal order. And what we see is, again, two equally stable states because we're at a transition point. These equally stable states are a state of low crystal order and low nematic order, the melt, and high crystal order and high nematic order. Now we have a movement in crystal order as well, not only nematic order. And what we see when we compute the minimum free energy path is a really movements in both, right? You need not to move straight up or straight, right, straight east. You need to move cooperatively in both crystal and nematic order, which that was surprising. We didn't expect that, both theories that I'll show you later. I'm jumping the gun here. So the other cool part, and we can talk about this if you all like later, but I can extract like a free energy barrier along some collective variable, and really that's pretty cool. The reason it's pretty cool is because to compare with experiment, what people measure in experiment is nucleation rates, and that's directly related to the free energy barrier. Here you have a little more on that. Let's touch on it since I've got a slide. Essentially, what we see is, of course, as volume fraction changes, the free energy barrier is expected to increase. But importantly, this is what I was kind of telling you all before, right? The time of crystallization or the nucleation rate is dependent on this free energy barrier. Actually, the induction time, but we can touch on that. And it enables comparison to experiments in molecular dynamics. That's important. And another cool thing for thermodynamic buffs is just note how nematic transitions are lower than a KBT. What does that tell us? That tells us that nematic transitions happen through just random thermal fluctuation, which is in the order of a KBT, right? Whereas if you were an isotropic to a crystal transition, you are above a single KBT and therefore highly improbable to happen without any perturbations at the melting point, right? That's why in experiment, what people do is they don't take it to the melting point, they lower the temperature a lot so they can lower this barrier. So, and another way to think about it is the isotropic to nematic transition is instantaneous, whereas the isotropic to the crystal transition will have an appreciable induction time before you see crystallization. Anyone can see that really by cooling ice past cooling water past 0 degrees. What you'll see is that it doesn't crystallize right away, right? It needs some time, and that's really that induction time before a crystal can form. Funnily enough, seems like forever ago, when we first submitted this paper, we got a review back that was titled "This work opens more questions than it answers," and that's forever going to be my favorite review because we think it does, right? Right? You have these interesting results that tell you a story. Of course, it's a very simple model, but the story is quite fascinating. We didn't really expect it, and this gives you a recipe for analyzing bigger systems, more accurate systems, and such. And really, what we see is that pneumatic and positional order increase cooperatively in this crystallization mechanism. So how general are these conclusions, right? That comes to mind when you think about our inputs. Our hard rods have this unique nucleation. Maybe we have a different nucleation for, I mean, is it general? Who knows, right? How sensitive are these results to intermolecular potential? How soft the beads are, right? Movement on the length scale of the bonds, having a continuous stiffness instead of a discrete one. Are our chains long enough? Are there finite size effects? All that stuff. So really, this concludes the first part of the talk. I hope I'm not. Uh, it's been an hour, almost an hour already. Man, I'm chatty. Um, all right. Well, do we have any questions? All right. All right. All right. I'm glad you think so, man. So these chains, um, they're uh, they're 20 long, and each of them is four. So really, we're simulating is an oligomer, not really a polymer, and that's an important thing to mention. Maybe I should mention that uh, earlier, but that's important, right? And that's why we say it's for a system of simple semi-flexible oligomers. And we expect there to be some finite sized effect. Uh, but that's on our mind, and we want to simulate bigger systems. But these systems, they take forever to simulate, right? So we didn't want to start we didn't want to start um, with these low uh, um, with these oligomers. We'd much rather answer the question directly. Unfortunately, um, or fortunately, you always start off investigating the simpler answer.
Oh, absolutely.
So,
Yeah.
because well, I mean, funnily enough, that's not what we did. But
Okay.
maybe we'll have a chance to touch on that later. I have some slides to to discuss that.
Okay.
And if you're interested, Kumi Chanak, please refer to the paper, and there will be accurate information,
Yeah.
particularly in the SI.
I,
All right, so let's talk.
let me
Yeah,
ask one more question real quick. Just this
sure.
may be like we'll come back to it and answer it later. Is this method of is this method of simulation applicable to polymers that are different from the polyethylene? So something like even like PTFE or some other polymer that's not like, let's say, a saturated hydrocarbon like this one is. Is it
Yeah,
can it be broadly applied? Even if you have to make some modifications or whatever, is the general idea the same, or would you have to change it up?
yeah, yeah. I think so. Well, of course. Here's what's up, right? Let's look at the model. So really, anything you can think of that you can do with the model, people
Hmm.
have done,
Okay.
right? And really, what you do now is instead of just having all gray, um, beads, you'll have different colored beads. And what that means is basically they just have a different interaction. Now, with this model where you have hard spheres, you can control that, right? What you can control is sigma right here,
Okay.
right? You can change sigma, their size, which will make them behave differently.
Okay.
And people have done that, right? So there's many situations where you'd want to do that. Maybe like a bigger, bulkier polymer or a polymer with a with a um, with a branch.
Hmm.
Um, but also, Ben, you could really have atomistic polymers where you define, you change up the hydrogen with a fluorine, right? And you define
Yeah.
how they interact with each other. You define that through what you know from quantum mechanics. What are their average bond lengths, you know stuff like that. And that's really atomistic is kind of the closest answer you're going to get to true, right? And then we can do all sorts of tricks to simplify the model and get more expedient results. You basically with molecular simulation, it really is optimizing, right, accuracy and expediency, and those are unfortunately almost always uh, uh, neck to neck, right? So
Right.
so uh, so what you're gonna do is try to reduce the accuracy to an acceptable level um, while maintaining uh, well reduce the accuracy to get uh, faster results while maintaining an acceptable level of accuracy,
Okay.
right?
Yeah, that makes
Um,
sense.
and for crystallization, at least the crystallization that we're interested in, at a first approximation, we care much more about how the chain behaves than how the carbons and hydrogen behave, right?
Okay,
Now
I
that
got you.
picture would change much, much more if you had hydrogen bonding and things like that. But in this system, that degree of freedom is not all that important. Now, there are degrees of freedom that are important that I'm neglecting. For example, we know that chains, they have like cis and trans states, right? So
Hmm.
when I go and lump a bunch of carbons together, that's gone, right?
Sure.
Um,
Okay.
so
Okay.
so I can't get things like folding, right? Which is important. We know that. So,
Okay.
if we look at these crystals, right, that I've drawn here,
Hmm.
what you see is a folded crystal, right? I
Right.
can't get folding. My polymer doesn't care. It just wants to be stretched out. It doesn't care about folding, right?
Got it.
Whereas
Okay.
if you have these cis and trans um, angles, now you have like a preference towards the cis and it can fold. Actually,
Okay.
the preference is towards the trans, but the cis is accepted, and that's
Okay.
why it folds.
Interesting.
To TMI, but ultimately, let's see, where was the question? The question was, can we do other kinds of polymers? Yes, and in
Yeah.
fact, we are planning to collaborate with some collaborators to simulate bottle brush polymers. Have you heard about those, Ben?
Bottle brush polymer. No. I mean,
I just want to show you a
I'm
picture.
assuming, yeah, I'm assuming that it's like a central chain with a whole bunch of stuff coming off of it, but
Well, it's kind of cooler.
oh,
Can I can
yeah,
I
yeah,
stop sharing
yeah,
for a
yeah,
second?
yeah,
Is
absolutely.
that okay?
Yeah, please.
All right, let me pull up Google here because those are pretty cool, and that kind of answers your question
Yeah,
because you've
absolutely.
had got all sorts of molecular. Um, I mean, I guess how you described it is pretty good after all.
Okay.
Um,
I'm
that
always
I'm looking
interested to
at
see
it.
that though.
Yeah, let me pull it up. Oops. Um, All right, let's just share screen here. So these are bottle brush polymers. So you've got basically much like you described, right? You have a
Okay.
long chain here, and
Yeah.
then you have things sticking out of it. But interestingly, right, as you can see here, you can also introduce different kinds of polymer beads in here, right? Or a copolymer or something like that.
Yeah.
And that, inspires all sorts of funky stuff.
Oh,
Um, yeah, and
okay.
I'm by no means an expert on these simulations, but you can do these simulations, right? All sorts
Sure.
of interesting simulations. Um, yeah, so I hope that answers the
Very
question.
cool. Yeah.
Yeah, do we have more questions? I see.
I think that's it for right now.
Oh, okay. All right. That's good. So, all right. I don't want to put anybody on the spot, but do you think there's value to like asking folks to Well, that's all right. Okay, so let's look at the effect of model selection on nucleation and polymers. So here I kind of asked like, how general are our conclusions? How sensitive are we to the potential model? Blah blah blah. Um, so let's answer that question. That's the fortune of I guess this being in the past is I have some answers, and I want to motivate this again. So we've seen this before, right? Have we? Oh, we haven't. Cool. I guess I skipped that slide. Um, it's not cool. Did I really? All right, whatever. So usually people answer these questions as I've told you via non-equilibrium molecular dynamics, right? So essentially what non-equilibrium molecular dynamics is, you put stuff in a box and you solve it like you're just like you're solving Newton's equations of motion. Okay, so just imagine you have cars and you have their speed and acceleration, predict in time where they're going to be at the next stage, right? And the reason you can't solve for large amounts of time is because you have collisions. Basically, these beads get close and they interact with each other, and you want to solve for a small delta t. That's what molecular dynamics is, right? So the reason we like molecular dynamics and the reason most people default to that kind of simulation is because you're just solving Newton's equations of motion. As long as you are introducing correct ways that things are interacting with each other, you should retrieve um, the behavior of the system, right? It's quite a powerful way of answering questions. So essentially, the controversy comes from having these two simulations, well, multiple simulations that give us different results, different insights into how polyethylene crystallizes. So in non-equilibrium molecular dynamic experiment one, funny enough, when I last talked about this, the author of the paper that I'm referring to was in the room, and I said we have this excellent paper here on the left, and I'm not just saying that because one of the authors is in the room, so it's that. So yeah, it still is an excellent paper, and I meant that. At any rate, essentially what they tried to investigate what the crystal nucleus is, what's forming from metastable melt, and that's what's in red here. And essentially, they found the cylindrical crystal nucleus. They found the crystal size is a good order parameter. They found no intermediate phases, right? They just saw the picture that we saw from classical nucleation theory, which is the one-step crystallization. On the right here, they saw we have a different experiment, right? A different simulation. And essentially, they saw a very, very different picture. The crystal nucleus was not cylindrical. Crystal size was not the only important order parameter, and that the crystal nucleated via inside a pneumatic droplet. Essentially, what that means is you have a pneumatic droplet in blue, and in the middle of it, the crystal nucleated. So essentially, that's what two-step crystallization is, right? Ben, can I stop here for a second and ask you, when do you want me to end this? Because I can go on.
Whenever you want. That's the no
All
no no
right,
real
let's
hard
just
time
keep
limit.
chatting.
Yeah, if it ends up being like
Okay,
one
thanks for
a.m., we might
listening,
start
Ben.
winding it down. But until then, it's all yours, man.
All
Go
right,
ahead. This is cool.
all right, all right, all right. I like that you're interested. Thanks, Ben.
Yeah.
Okay, so let's talk. So, what differences could account for this agreement? So again, I motivated it initially, and really I could just jump into this part without motivating it again. But I think this is interesting. So let's look at these two simulations. You know, um, of course, I'm not picking on anybody. Those are two excellent experiments, but they both say I'm simulating polyethylene, right? So what's the difference? Does the difference come from? So the difference is in the model, first and foremost, right? Here they have an atomistic simulation, right? So, well, it's not actually atomistic. They're lumping all like the carbon with the two hydrogens. So that what you call that is you call it a united atom simulation, right? So you have one CH2 per bead, whereas here they're lumping, much like me, three carbons in a single bead, right? And this is what we call a coarse grain simulation. And then we have a different kind of Leonard Jones, and we have a different kind of cutoff. I mean, there's a lot of important differences here, right? Additionally, they have this thing called the undercooling, right? We talked about if you put ice in the freezer and you get it to 0 degrees C, it's not going to crystallize right away, right? There's going to be an induction time. That induction time, imagine in this plot here, temperature versus time, the TC, basically where you hold your polymer, was close to Tm. What you'll find is that your crystallize, or your free energy barrier is massive, right? As we saw before, it's much more than a single KT, right? You're going to wait a long time for a fluctuation that is has enough high energy to overcome the barrier. I hope that makes sense. So what they do in these simulations is they use a large undercooling, right? They take it down to a very small, well, to a low temperature relative to the melting point. And not only that, as we've talked about, equilibrium is important. We want to study equilibrium, but also the undercoolings used between these different simulations are different, right? So these are the two sources of error. So what we propose, and maybe I should have had a slide for this, but again, I've already motivated this. What we propose is let's go back to the basics, right? Let's simulate a simple model that's tractable, and let's simulate an equilibrium, right? And that you cannot do that with molecular dynamics, but you can with Monte Carlo. So we start off, of course, with the where we left off, right? The hard spheres, rod bonds, and now we introduce a variation, right? Before you had these discrete chains, right? So you're either stretched out and you're not stiff, or you're kind of bent and you're stiff. And on the right-hand side here, you see continuous stiffness. So what does that mean? So now, and unlike the on-off behavior that we see on the left, now you have a continuous stiffness, right? As you bend more and more, you get stiffer and stiffer, right? So there's a larger penalty to how bent you are. And the more stretched out you are, the more you are favored thermodynamically. All right, so some more basics, right? We already talked about how the reduced temperature and the volume fraction are the two things that control the physics, right? Those are 2 degrees of freedom. All right, so let's look at some melting curves. So here you have pneumatic order, and it's really the same as Q6, but instead of going from an arbitrary range, it goes from 0 to 1. What we see here is what we saw before, right? For the discrete system, the discrete stiffness at a single temperature, right, at the melting point, what you see is you go from low P2 to high P2, and you go from low crystallinity to high crystallinity, right? It's a single temperature, it's a single transition at a single temperature from the melt to the crystal. What happens when we switch to continuous? All right, so what we see is a similar picture, right? At some temperature, both increase, right? But that temperature is different, right? So now what you have is you go not from the melt to the crystal directly, but rather you go from the melt to the pneumatic phase to the crystal. So you're crystallizing via the pneumatic phase. Interesting. That really looks like the SOM hypothesis that we saw before. So let's investigate this further. Of course, a more concise way of putting all of this is via phase diagrams. So let's look at the phase diagrams. On the left is nothing strange. We've seen that before, right? High temperature, any volume fraction, your isotropic melt, you cool it down, you will form order. If you're below the phi crest, you go from the I to the N. And if you're above it, you crystallize to the crystal. Now, when we look at the continuous stiffness, we see a very different picture. At low enough phi, you have the same picture, I to N. At high enough phi, you have the same picture, I to C. But there's this little envelope, right, where you have an isochoric two-step nucleation, right? You start with the isotropic phase, then at some temperature, you form the pneumatic nucleus, and then finally you form the crystal, right? This is kind of what we saw here, right? You have the isotropic, inside it, there's a pneumatic phase nucleating, and inside it, there's a crystal. All right, interesting. So why does this happen, right? I mean, that's an important question. And we can kind of guess why, right? The only thing we're changing is the stiffness potential model. But let's look at this from a physics perspective, right? The physics is controlled by the persistence. So we've talked about that. We touched on the persistence length before, but I really explained it correctly. Persistence length is essentially how long are there associations. Think of an autocorrelation function, right? It's kind of like an autocorrelation function of the angle of consecutively bonded beads, right? So let's take a minute to appreciate that. At a persistence length of 20 or 100, right? What that means is that 100 beads along the backbone are feeling each other. Okay, they're kind of stretched out. their positions are correlated. Their angles they form an angle that is stretched out. Okay, that's kind of what it's telling you. I mean, that's not the most accurate description, but essentially, the higher the persistence length, the stiffer the chain, right? So what we see, of course, at the highest temperature is that both models give you a low persistence length, right? So what does that mean? You have a coiled up polymer, right? There's no incentive to pneumatically align or to stretch out, right? As you decrease the temperature, both models, the discrete and this continuous, give you a persistence length increase, right? They both motivate a persistence length increase, but there's different behavior. Let's start off with the discrete. We've seen that before, right? There is sort of like very on-off kind of behavior. At some temperature range, you have an increase all the way up to some persistence length, but then it plateaus, right? So why? Well, here's why. It's an on-off thing, right? You get to a temperature where now there's a driving force to become off, in other words, stretch out, but past the fact of stretching out past that on-off cutoff, there's no longer a drive to crystallize, right? Whereas with the continuous stiffness, right, we don't have this. We don't have this kind of behavior. As you lower the temperature, it's still going to want to continuously give you a driving force to further align, right? And essentially, what's happening here is that at the discrete stiffness, you have a single kind of step change to a very high um, alignment. And at that step change, basically what you're going to have is a lot of these chains are aligning, and it's going to force the chains via crowding to either crystallize, or maybe it's a low enough density that it doesn't. Whereas when we're looking at the continuous stiffness model, what we see is that as you lower the temperature, it's going to keep getting stretched out more and more, and that's why we see that eventually it crystallizes. There's no like single jump that is going to inspire a large entropy penalty. Rather, you have a gradual pneumatic alignment that eventually, at a lower temperature, inspires a crystallization. So that's kind of the picture. Now, tell me this isn't a good TOC figure. You're fine. You can tell me it's a bad TOC figure, but this is the TOC figure of the latest paper, right? If you have a discrete bending stiffness, you have a single step nucleation. If you have a continuous bending stiffness, you have a two-step nucleation, right? Thank you, thank you, thank you. I mean, listen, even if it wasn't, you'd have to say that. So I don't trust you. All right, I guess we'll see if the paper gets accepted. So we're submitted a letter, and we hope it does. So, all right, a natural question. We can stop here if you've got questions, Ben. Mm, mm, mm. Yeah, 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 yeah. Good question. So we can, as you can imagine, a lot of these things we're not actually measuring. I think maybe a way to put what you're saying is like the coordination number, because what that
Yeah.
means is like how many. No, right, and we can't measure it directly, right? But there's ways that people measure it.
Okay.
So I'm not sure how you would do that. But like imagine scattering, right?
Hmm.
So scattering can tell you a little bit about that.
Sure.
Scattering, tells you basically if they fit into a lattice, which can tell you a little bit about the coordination number. Um,
Okay.
yeah, but I'm not sure how you would calculate that. But it's going to be something like that.
Hmm.
Um, where you have and really when we're talking scattering, right, it's all about how much it's going to scatter versus how much it's going to whatever, right, sense that signal. And you can have all sorts of other types of scattering that, for example, would scatter more if you had alignment or things like that. So we can get
Sure.
much from experiment. but I'm by no means an expert on experiment, and I'm glad I'm not.
Yeah.
I'll leave that to experimental collaborators.
Fair enough. Okay. Appreciate it.
Yeah. All right. Yeah. You know, um, all right. Let's proceed here. So let's talk about the effect of the. Well, here's what's up. Right before we looked at this, right? We looked at what happens when we change this degree of freedom. Let's look at what happens when we change the two others, right? So instead of hard spheres, we introduce soft spheres. So what does that mean, right? They their barriers aren't really solid, right? So what that means is they can overlap, right? The hard spheres, they either don't overlap or they do overlap. So now we're introducing softness, right? So one may ask, why do I care about softness? Well, first of all, these aren't really like atoms, right? They're actually um, combinations of atoms, which means that effectively, if you're trying to simulate them more accurately, they should have a um, soft, squishy boundaries, but also this is soft matter, right? The atoms don't have rigid, um, um, rigid repulsion, right? It depends on temperature and all that stuff, and as you increase temperature, you're going to have more and more softness, right? This is soft matter. That's why softness is important. And another thing we can release, of course, as you can imagine, is the fact that we're not using rod bonds. Instead, we're using spring bonds, right? So what that means is that you have fluctuation on this length scale of the bonds. All right, and then a continuous stiffness. So let's see what happens. So now we've introduced, of course, another degree of freedom, yet another, which is the stiffness strength, right? And the reason, well, we can talk about why that's introduced, but now you have an energy associated with the stiffness, but also an energy associated with the softness. So that's why I guess it's simpler than I was putting it. Surprise, 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 surprise. To my surprise, if we correctly account for phase behavior, the phase behavior is universal. Isn't that plot on the right so freaking cool? And again, you are contractually obligated to say that it is cool. Let me describe it a little. So you have volume fraction on the left-hand side and reduced temperature on the bottom here. And this is what we've seen before, right? In fact, the hard bead kind of the boundaries that you've seen them before. Those are actually those of the heartbeat, right? So we've seen it right here, right? This is the heartbeat phase diagram, right? You're just seeing that again, but now uh, I've put on top of it not only the heartbeat scatters, but also scattering from soft beads at different stiffness strengths. Because remember, now we have that degree of freedom. And now what we see is it's a mess right here. But essentially, if I account for the softness of the spheres, right? If I account for that, if I correct the volume fraction for it, what I see is that all of the data, regardless of the softness, regardless of the stiffness strength, collapses onto that of the hard sphere. What that tells you is that those degrees of freedom, unlike the stiffness, right? What did stiffness do? Stiffness, it's a mess, right? Those two phase diagrams are different, right? Whereas when you look at the effect of the two other things, if I properly scale it and account for the difference of the soft bead, essentially it's only inspiring a shift, nothing else, right? So properly scaled phase behavior is universal, at least on these two degrees of freedom. In fact, I should have changed that. But really, it does open more questions than it answers. All good research does. And essentially, what we've learned is that the stiffness model selects the pathway, whereas softness and stiffness strength are far less consequential, right? Um, if you use reduced temperature, that corrects for the varying stiffness, and if you use the effective volume fraction, that corrects for the varying melting temperature, right? At varying at softness, at varying softness. All right. And the cool part, right, is now, initially we had the discrete kind of unique cooperative nucleation that didn't really fit either model. But now we have the continuous stiffness model, which it does look like it agrees with some, right? It tells you that First, you have a transition to enigmatic phase, again, dependent where you are on the phase diagram, and then you have a transition to the crystal. So that's kind of interesting. It'll be interesting to go back and build the free energy landscapes again, and from learn stuff from there, right? And of course, I refer people to the papers that we've got. We've published in the Journal of Chemical Physics, and we're working on publishing the next one as a letter. So what's the consequences to polymer theory? How general are these results? Of course, that's the salient question, right? What will happen if you have longer and longer chains? What will happen if you have, dihedrals or attraction between beads? Of course, attraction would encode things like, the van der Waals attraction, things like that. How important is that? Now, there is some literature that suggests that isn't as important. And finally, is stiffness more important than connectivity when it comes to crystallization or not? Here's those results again, right? So discrete bending, you have this picture that we saw before, but when you have other semi-flexible models, more accurate ones, you see separate phase transitions with lower barriers. And of course, this is, I guess I should just remove this, but here's some more interesting questions. All right, so this is the last one about GPU accelerated Monte Carlo, but we don't have to touch on it. Basically, really quickly, I just cut up my simulation box in a way that allows me to do multiple smaller simulations in the same box at the same time. Really interesting. Many people have tried it, not many with polymers. The reason they haven't is because that often fails. I don't get good enough speeds, right? No matter how hard I try. And you can see the number of polymers here, and each polymer that we've simulated here has 1,000 beads. So I was like trying to defeat a monster that I had no means or business messing with, right? And what we see is the speed ups are nowhere close to give me access to things that people haven't seen before. So that's kind of my PhD dissertation was a bit of a nightmare, as most are. You're learning so much and all that stuff, and for me, the big dragon I had to slay was this pivot from the initial motivations to what we ended up doing, which I'm actually quite proud of. Here's some acknowledgments. Here's my lovely PhD advisor, Douglas R. Tree. Here's some undergrads I worked with and some graduate friends. And of course, I thank our funders, the PRF, the Petroleum Research Fund, and the Office of Research Computing for computing resources. And I think that's that. All right. I'm going to assume
Very
that
cool.
there's a crowd that's clapping.
Yes. Yeah, that's super cool work, and we actually have a few questions, so we'll go through those real quick.
All
So
right.
for the stiffness models, does each one have its own best case usage, or is the continuous one generally better than the discrete one?
Good question. The latter, right? So here's where the discrete stiffness model is better. It's faster to simulate, right?
Okay.
It's much easier. I didn't have to, do as many experiments with discrete stiffness.
Mm-hmm.
It was much easier to simulate, right? So really, it's all about whether you are, whether you think that order, that length scale, or that the accurate bending
Mm-hmm.
is important or not, and that's really the interesting part. Maybe I don't know actually. Maybe I shouldn't answer that question as confidently. Maybe there are some like very stiff polymers that encounter some sort of
Yeah.
on-off behavior.
Yeah,
So I don't
I
know.
can see
I
that.
don't really know.
And you make a good point about the ease, or I guess the computational time that's involved in doing the discrete one. Yeah, I mean, I'm sure there's probably, like you said, there's probably some cases where the discrete one, even if it's not 100% accurate, it hits that good enough level for certain cases, where the trade off of going to the continuous model maybe is not worth it.
Right, plenty of cases. Ben, we didn't invent the model. Of course, it's
Sure.
abundant in the literature, and in fact, sometimes used to study crystallization. The
Okay.
paper that we started with was doing that. And yeah, I think we got the full picture on that question.
Okay. Let's see. Could the model, I think just generally, could the model be extended to predict physical properties beyond crystallinity? So things like pore size, or selectivity of ions that are transported through say like a polymer membrane, things like that.
Hmm, that's a great question. Yes, you can. You can study, batteries. You can study membranes. Um, you can study semi-permeable membranes, right? You can, and it's all how you define your beads, right? So
Okay.
you can um, much like we define uh, the bead softness or maybe the bond angle, define um, uh, you can define ways that charges interact with each other. Um,
Hmm.
but even as a simple kind of first order approximation, you can make things that are charged be more attracted to other things, right?
Okay.
And by that way, you can simulate, a charged polymer or maybe even a polymer that is in a charged solution, right? Like with ions like salt, and
Yeah.
then you can study basically how it like phase phase separates into a part that likes water and then a part that doesn't like water. And
Right.
yeah, you can do all sorts of stuff. Molecular solutions are exciting, and
Oh yeah.
the
Absolutely.
questions that you can answer are really abundant.
Okay. Interesting. Okay. And let's see, I got one more here for you. What about smaller molecular weights? I would expect the pneumatic phase to vanish for sufficiently small change, but do you have any idea whereabout that might?
Yeah, good question. Um, I mean, good question. As you get smaller, right, it's going to become less and less important. That being said, that degree of freedom, as long as you have three, will still be important, right? How
Mm-hmm.
important is it going to? Are you going to have some sort of transition? I don't think so. Um, when you stretch out, really, it's all about the balance, right? Of the system as you decrease its temperature,
Mm-hmm.
the problem is it's going to become contacts between beads are going to become less and less favorable. As you reduce the
Okay.
temperature, it's going to want to fit as optimally as possible, right? What
Mm-hmm.
that means is it wants to minimize the surface contacts it has. To do that, right, it has to kind of fit in a perfect lattice,
Makes
right? So
sense.
as you reduce temperature, it's going to want to do that. And the longer your chain, the more you'd have to become aligned to make that perfect kind of fitting into a
Okay.
lattice, right?
Yeah.
So it's all about whether it needs to stretch out to do that or not. Um,
Okay.
yeah.
Yeah, that makes
So
sense.
so in small molecules, right? Like if you had something like ice, pneumatic behavior doesn't matter, right? Ice is just it's H2O.
Yeah.
That's not going to matter. Um, uh, yeah.
Interesting. So I'll give just another quick chance. If anybody wants to get any final questions in, but I'll go ahead and say this was super cool. I learned a lot.
Yeah.
This was really neat to learn about, and I appreciate you sharing it with us because, like I said,
Well, yeah. Thank you.
I'm always I'm definitely on the experimental side of things. So anytime I can learn about computational work, I'm always excited to do that because a lot of it is just completely over my head. But you did a really nice job of explaining
Well, thank you.
what
I
you were
appreciate.
doing, and I'm sure it's not simple, but it's very complex work. But you did a great job of explaining it in a way that someone like me can understand. Uh, but yeah, this is
Yeah, that
really
was the
neat
goal.
stuff. So I think it looks like
Yeah,
that's
I'm
all the
glad to hear
questions we
that.
have. So I'll say thank
How
you
long have we
again.
gone? How long have we gone for?
Let's see, about an hour and a half, roughly. A little
Okay,
bit
that's
less than that, so
excellent.
that's good.
So I'm looking through your YouTube, and I think this is the longest episode you've
It
had.
may very well be. Yeah, I'm gonna have to go and see there. I know there was one other talk that I know went for more than an hour, but I'm not sure if it was an hour and a half or not. So We'll have to see. I'll let you know.
Oh, listen, you got to keep me here for another 30 seconds. He's got
Okay.
one, someone's got 147.15. All
Oh
right.
man. Okay. Yeah.
I'm almost there. Okay.
Okay.
I'm almost there.
All right. Well, so all right.
All right.
So
What an honor, though. Thank you, Ben,
yeah,
for listening to
absolutely.
me, and thank you everybody for coming. This was excellent. It's always a nice opportunity to talk about my science. My faculty advisor likes to say a prerequisite to getting a PhD is liking hearing yourself talk. So on that
Very
note,
true.
goodbye, everyone.
Yeah, it's yeah, that is surprisingly true. That's definitely something you got to get used to doing. Um, but
All right.
yeah, so thank you again, Pierre. Let me get you to hang on for just 1 second, and we'll just talk very briefly. And for everybody else, thank you for coming out. I don't know. I don't think we have a talk scheduled for next week, but follow me on Twitter at Meekins Lab, and you can find out more about it there. You can also follow Pierre at Pierre Kawak, right?
Yeah, I think so.
Okay.
Ben, I'm sorry. Have you ever done one of these? Maybe you need a guest host.
Possibly.
All right. We'll talk about it.
All
Anyway,
right. Sounds good.
thanks, everyone.
All right. Bye, everybody. Have a good night.